Good morning, and I would like to thank Barbara and Guillaume for inviting me. And I think I'm going right on from Dan's talk now in looking at seismic structures, or also Hust's question, whether they can be explained by post-perovskite or by a phase change. So what do we have to do? We really have to look at seismograms. And if you look at real seismograms, we have seen all kinds of tomography models recently, but if you look at real seismograms, you can see that they are actually quite difficult. You can see here an S wave, here an SCS wave, but you have all kinds of other things in between that may be very difficult to explain, especially when you look at a homogeneous Earth where there's nothing in there except for mantle, outer and inner core. Then you would expect basically a P wave and a PCP wave, the reflection from the core mantle boundary, but nothing in between. Or you would have the PKP waves. So what can we do to explain these wiggles that we have just seen between S and SCS or P and PCP? We just add layers in the Earth. And for example, in this case, we have the D double prime layer. And when we have a reflection of that layer, we get an additional phase in our seismogram. So you have the P wave and then this thing that we call PDP because it reflects off D double prime and then PCP here. And we can do the same thing everywhere in the Earth, so we can add upper mantle discontinuities and get more reflections. So I am actually going to look at these reflections that we see in seismograms, or the additional wiggles. But going back to the lower mantle and the structures that we have in the lower mantle, there was some talk about the large low shear velocity provinces under the Pacific and under Africa, and whether they have steep sides, flat tops, sharp edges, and questions like that. These things have been looked at and modeled recently, and that's one of the big observations there. And the other one is very small scale structure, and unfortunately it's not in Sebastian's talk, even though we thought it would be there. These are small scale structures at the core mantle boundary, about 40 kilometers or so high, a few tens of kilometers or hundreds of kilometers wide, with a reduced velocity and increased density. Mike already talked yesterday about anisotropy in the lower mantle. There's lots of observations of anisotropy in different regions, mostly here in the Circum-Pacific, but also some observations that are, I think, a bit more difficult to explain here in the Central Pacific. But I'm mostly constraining myself to the reflections of the top of D double prime, so the PDP wave. It should look like this. You have the P wave, PDP, and PCP. And because you can already see that the wave is arriving with a different angle at the surface compared to P and PCP, that can be translated in something called the slowness. That's shown here. The slowness is, well, basically, translates in the angle of incidence. And you can see this at the different move out in the seismogram as well. So here we have P, we have the PDP wave, and PCP is barely visible. But when you stack the data in different angles of incidence or different slowness values, then you can see here's the P wave, you can see PCP, and in between you can see a wave that arrives with a different slowness between P and PCP, and a travel time between P and PCP. And that's a way of discriminating between, say, reflections from other discontinuities and reflection at the D double prime discontinuity. So we can actually detect our reflections and use the slowness and but also amplitudes and polarities in this case. So I'm going to look first at high velocity regions because that's where most work or most studies have actually found these D double prime reflections. So I'm looking at, or I'm using data from Siberia here, from Southeast Asia, and from the Caribbean. And this is a study, or it's a compilation of different results from different people. It's based on the work by Session in the AGU monograph. But you can see lots of observations of S reflections at D double prime and a few observations of P wave reflections. That's the blue ones. Okay, so what are the observations that we have in these high velocity regions? Well, Dan already mentioned the double crossing model. So what we actually find in these high velocity regions is up to 2 reflectors. Here, this is an example from Eurasia. an upper reflector that has a lot of topography, and a lower reflector that seems to be much flatter and only like, well, 50 to 80 kilometers or so above the core mantle boundary. A similar picture is found in the Caribbean. This is the upper reflector here for S waves. You see a lot of topography. Here it's about 400 kilometers high. Here it's about 200 kilometers high, and in between there's this topography. And a lower reflector here in the same region. And for P waves, you see the same thing, an upper reflector about 400 kilometers high and a lower reflector about 100 kilometers above the core mantle boundary. And in Southeast Asia, you have a similar picture. So that's one of the observations, that we have two reflectors in these areas. And the other thing that we're looking at is the polarity and amplitude, or in this case, the polarity of the reflection. If you look at the Caribbean here, if you really look at these wiggles, then you can see for PCP, there's a downswing and an upswing. It's maybe better to see here in Southeast Asia, a downswing and upswing, but this PDP reflection that we can recognize by its slowness and travel time between P and PCP, you have an upswing and then a downswing. So you have an opposite polarity of the PDP compared to the core mantle boundary reflection and the P wave. So that's for the Caribbean and in Southeast Asia. For Eurasia, for the P wave, it's actually the same way. So here you can see downswing, upswing, downswing, and here the same for PDP, downswing, upswing, downswing. So we have the same polarity. But if you look at the 45-degree path compared to this one, east-west, and there's another north-south path, then you can see that it's, again, here the opposite polarity. Actually, here you can see it between P and PDP. It's opposite polarity between those two waves. In the S waves, you see in all cases that the S wave reflection of D double prime has the same polarity as SCS and S. So that's, of course, very interesting because in some cases, and these are all high velocity regions, right? In some regions, you see a P wave velocity decrease and an S wave increase, and in other regions, you see increases in P and S waves. So this is just summarized here in this slide. In Caribbean and Southeast Asia, you have that kind of scenario, negative P wave impedance contrast and positive S wave impedance contrast. In Eurasia, you have positive impedance for P and S for two perpendicular paths, north-south and east-west. And for a 45-degree path, you have a negative P wave impedance, or velocity increase. And the difference between those two regions for me was that you have, well, these are the travel paths, north-south and east-west, and this is the 45-degree path, and admittedly it reflects in a different region. But it's still in this high-velocity region. And for the Caribbean, this is the path, and I've also shown here the plate motion for 80 to 100 million years ago, basically looking at how the plate has gone into the lower mantle. So there are lots of explanations for this D double prime discontinuity that have been presented in the literature recently. One of them is the top and the bottom of a purely thermal slab, but also there's this birth of an upwelling. There's thermochemical boundary layer with internal low velocity zones or other things. There could have been a change of anisotropy with depth, but also the post-perovskite transition that Dan just spoke about. So I'm looking at post-perovskite by the magnesium silicates, so I'm sorry I'm not using pyrrolite, but this is for us at the moment a bit easier. So there's a few of the values that you have. The density change was reported to be around 1%. It may have changed. The velocity change apparently is quite difficult. Motohiko said at some point it's 0.5% for S waves, and P waves weren't that clear. And the Clapeyron slope was in the region from 6 to 13 megapascals per Kelvin. I think that has been confined a bit better now. But the seismologists were all very happy when post-perovskite was found because it could explain so many different things. It could explain this reflection of the double prime because of the density contrast. It could explain anisotropy in the lower mantle because of the layered structure. And there were studies that it could explain the ultra-low velocity zones, but I figured out yesterday that it may not be the case because it would all be molten down there. But what it can explain is the two discontinuities, and Dan already hinted on that earlier. We have the post-perovskite stability field and perovskite stability field, and then depending on the temperature in the mantle, you can either get an entrance into the post-perovskite field and possibly coming out again, which would lead to two reflectors, or in a hot mantle you would not get into that stability field of post-perovskite at all. So it can explain the two reflectors that we're seeing in P waves and S waves. It could also explain the polarities, the PDP, the negative PDP that I showed earlier in some of the regions. So we have a positive S wave contrast here and a negative P wave contrast shown here, and this is work by Wookie and co-authors in 2005. And it can explain the strong topography that we see in the upper reflector, because depending on the temperature, the phase transition is higher or lower, if you just use magnesium silicates, of course. So if we look at these directional dependencies on the polarities that I showed earlier, so you have, in Eurasia, you have these two paths, the north-south path and the east-west path, that showed a positive P-wave contrast and a positive S-wave contrast, but a negative P-wave contrast if you go on a 45-degree angle. Then you can explain that by anisotropy of the post-perovskite phases. And we have done several calculations here. In this case, we have post-perovskite isotropic to an anisotropic post-perovskite, and then in the lower case here, from post-perovskite into from perovskite isotropic post-perovskite perovskite to anisotropic post-perovskite. And what's shown here is also the directions of the waves that we look at. E0 is the north-south direction in Eurasia. E90 is the east-west direction in Eurasia. E45 is the 45-degree path, and C30 is the direction in the Caribbean. And what you can see here is that this is actually reflectivity shown here. So blue is a positive reflection coefficient, and reddish is a negative reflection coefficient. So here you would expect a positive polarity for PDP. Here you would expect a positive polarity for PDP, which is what we're seeing. And in these directions, you would expect negative polarities for PDP, which we're seeing. And for the S waves, if you look at this case, these dashed lines, that's the overcritical reflection, so you get really strong amplitudes. You see positive reflections in all directions, which is actually what we're seeing. You can also see that the amplitude seems to change depending on the direction that you're looking at. With respect to the slab flow direction, I should have said this, the direction of the slab is considered to be in this direction. So just looking at our possibilities to explain the seismic observations, top and bottom of a purely thermal slab, I think we can rule out, because in this case we would have very, the reflection would not be visible for short period waves, because the transition from the normal mantle to the cold slab would be so wide that you wouldn't get any reflections in 1 Hertz waves, and we do see them. The change of anisotropy we checked, and I didn't really see very much in the data that I looked at. So I can't really rule out this part yet, but it looks like post-perovskite can actually explain our observations for the double prime reflector. But have we solved all the problems now? Well, I don't think so, because one of the things is that actually the shear wave velocity contrast is actually supposed to be small, and I don't know how big it is in Moore or Harzburgite, but I think Dan said 1 or 2% would be possible for S waves, so P waves might be very small. But what we can actually see is that the amplitude of this reflection that tells us something about the contrast possibly is actually very variable between different regions and different events. So the other thing is the sharpness of the transition. But John already showed yesterday some results from Aman et al. 2010, where he said that shear-induced alignment of the post-perovskite phase could actually produce a sharp reflector. And this is Dan's result from just now. So apparently we are able to get a bit of a sharper reflector than the work by Catali in 2009. But one of the other things is that we always look at D double prime, and already Dan put this nice little bar in there, D double prime reflector in the mantle, and we usually assume it's in about 300 kilometer steps with some variation. But recent work by one of my students shows that if you do it, this is 2.5D modeling with Terre, and if we have a flat reflector in 250 kilometers above the core mantle boundary, just a thing like that, and then we have a 10-degree inclined reflector at 140 kilometers above the core mantle boundary, then what you're actually seeing is that the travel time and slowness of these waves, of the reflection of D double prime, is actually the same. So just from purely looking at the times between S and SCS, or S and SDS, or the reflection, and SCS, the reflection from the core mantle boundary, doesn't actually help us to constrain the depth of this discontinuity. So possibly we're not in 400 kilometers above the core mantle boundary, but maybe only in 100 kilometers above the core mantle boundary if we have not flat reflectors but inclined reflectors. So just looking at the low velocity regions, and I'm looking at two regions, one that has been studied before by Thornley and many co-workers, and another one here in the Bering Sea. And if we look at this low velocity region under the Bering Sea, we find reflections of D double prime in one region here. These big round circles are about 300 kilometers above the core mantle boundary, and then they become apparently lower in 150 or so kilometers. And then we have a region where we don't see any reflections, no matter how we filter. So apparently we have something that is like a ridge or like a bump at the core mantle boundary. It's about 300 kilometers high and maybe 300 or a bit more kilometers half width. It's a low velocity region. The reflector is sharp because we can see it with 1 Hertz waves. There is possibly a second reflector in some of these cases visible, so possibly or not a double crossing. But we do see a positive P-wave contrast in this region, and that's a bit interesting because we have a low velocity region here. And it seems to be fairly steep sides. And then if we look at another low velocity region, that's this region in the Pacific up here. So we have earthquakes from Tonga, Fiji recorded in the US. And there was the study by Ley et al. In 2006 where they look at this region as well, and they find something like a lens shape reflector here that seems to decrease towards the edge of this low velocity region. They saw at least 2 reflectors, up to 4 actually, in a study by Ota and al., and they were explained as phase transitions in pyrolite, morb, and a ultra low velocity zone. We looked at the same region with our methods, and we do find up to 2 reflectors, but we don't see this decrease at the edge of this low velocity zone. But the reflections for the P and S waves seem to be positive in this region. So one thing that we thought about this is, can we actually look with the same method at lots of different regions and then compare the data and find one explanation for all of them? And so one explanation could be, is there post-perovskite, for example, everywhere? And there has been a recent study by Laura Cobden and co-workers where they look at the Mantle models, and they're trying to fit different models to it. And well, basically it's a comparison, a statistical comparison, but what comes out is that a model without any post-perovskite has the least best fit and is mostly rejected. Most models are rejected in this case. So all the others, I think Laura or Jeannot or other people can probably talk a bit more about that. But there seems to be sort of a need for post-perovskite in the Earth. So then we looked at all our data that we had up to that point. And so this is Siberia. I showed this before, then the Bering Sea, the Pacific, Southeast Asia, and the Caribbean. And we looked now not only at the polarity of the reflections, but also at the velocity contrasts or the amplitude of these reflections. And of course, amplitude is a big problem. I said this before, that anisotropy can change the amplitude very much, but also the gradient zone between the well, the mantle and d double prime, depending on how sharp this is going to reduce the amplitude. If it's wider, the gradient, the amplitude will be smaller. But we just basically we look at all these different areas and we treat them all the same way, and we come out with some some amplitudes or some velocity changes of 1 to 3% for P waves in Siberia and 2 to 3% for S waves. In other regions, we have 1 to 1.5% for P waves in the Bering Sea and 1 to 2% for SDS in the Bering Sea. And then in the Caribbean, we have a negative P wave contrast of about 2 to 3%. And we modeled all these different cases. And admittedly, it's a 1D modeling, but we have some idea about the velocity contrast. And then in Southeast Asia, again, we have a negative PDP velocity contrast and a positive SDS velocity contrast. And then we're looking at, or we're using these results, and we're trying to model those. So basically, there's a starting model, and then there's an end model afterwards, and the elastic parameters and the composition can vary within some bounds. And Laura created about 1 million models and looked at all these models and how they fit polarity and amplitude. And if you look at that, the first thing is the fit to MORB. So what's shown here is basically these are all the models. This is the number of models here. So color shows the number of models. Here's the change in temperature, and here's the change in MORB. So if you look at all the models, you have these two cases here. If you try to fit the polarity, and this is Siberia, Pacific, and the Bering Sea, and this is the Caribbean and Southeast Asia. So these are the ones with the negative P-wave velocity contrast, and that's the ones with the positive. Then you can see that a slight increase in MORB here and a lower temperature could explain the observations of the polarity, and here also a decrease, an increase in MORB can explain the polarities. But if you look at polarity and amplitude at the same time, you can see that basically the Caribbean cannot be fit with any of the models that we've been trying, and Southeast Asia is also very difficult to find any models that fit, whereas Bering Sea and Siberia and the Pacific is much easier to explain with an increase in MORB. So basically, we can rule out MORB as a cause for the reflection in the Caribbean, or we're actually less confident that it is a reason for the reflection. If we do the same thing with post-perovskite, this is now here the number of models, and here's the change in post-perovskite. You can see here again all models, then the fit to polarity only works for both scenarios or for all 5 regions. But if you actually look then at polarity and amplitude, you can see that in Siberia and the Pacific, there's very few models. This is the maximum here is 3 compared to here 300. And in the Bering Sea, there's only 2 models that can actually fit the observations, whereas in the Caribbean and Southeast Asia, post-perovskite can fit the observations that we have there of the negative P-wave velocity contrast and positive S-wave velocity contrast. So one explanation could be the kind of style of subduction. If you look at some of the tomography papers and you do cross-sections through the tomography under the Caribbean, then you can see that this slab seems to sort of fold back on itself, which would mean that MORB is actually at the bottom of the slab. This is just a possibility, very arm-wavy, but maybe this is true. So here MORB would be at the bottom, so we get the reflection of the top of the slab, well, actually the bottom of the slab here, but MORB is here, down here. And in Eurasia, the slab seemed to have gone down into the lower mantle without any folding, at least when you look at these cross-sections and tomography models in different ones. And then you would get a reflection if MORB stays connected to the sinking slab, you would get the reflections of the MORB rather than this area down here. And in the Pacific and the Bering Sea, it could be that MORB is an explanation for the reflections that we're seeing. So, but as I said before, we can't rule out other things. We can't rule out the anisotropy in post-perovskite because that gave us this difference in reflection coefficient as well. So to conclude all this, well, we do see in the D double prime region, we do see reflectors, we see anisotropy, ultra-low velocity zones, large low shear velocity provinces, and so on. But if you just look at the reflections in the high velocity regions, we see positive velocity contrast for S waves and varying velocity contrast for P waves, depending on which region we're at and in which direction we're looking. And the amplitude is between 1% and 3% in most regions if we use 1D modeling. The low velocity region, we do see reflectors in D double prime, so that would basically be something against the pure magnesium silicate model if these regions are warm. And we do seem to have a positive P and S wave impedance contrast or velocity contrast. And as a possibility for explanation, there could be the phase change from perovskite to post-perovskite if it's sharp enough, and that's the model from John Brothold is actually explaining the sharpness, but it should be anisotropic to explain the P-wave contrast changes. And a different cause could be that it's not actually just one thing for the lower mantle, but it's maybe we have an increase in MORP content in some regions, but post-perovskite phase transition in other regions. But also what comes out is that strong changes in temperature can also explain some of the observations that we have. Thank you.